Okay, good morning, folks. Let's go ahead and get started. A few reminders. We have our fourth quiz today towards the end of the class. And I have already your third quiz graded. The grades are already on Blackboard, and I have the answer sheets here. So after the class is done, you're going to step outside, and I can hand it back to you guys. I also have the leftovers from the first and second quizzes. So they are here. What we did last time was we started a new chapter, chapter 7, I believe, which is isolated DC to DC converters. The first topology that we analyzed was the flyback topology. It's quite simple because it only has one transformer, and the magnetizing inductance of that transformer is the main inductor of the topology. And then we have one switch, one cap, and one diode. As it turns out, the flyback converter is like an isolated version of the buck-boost topology. So the voltage transfer ratio is like D over 1 minus D, and there is the number of turns of the transformer is also appearing there, so it gives you an extra degree of freedom. The isolation provides you several advantages. For instance, you can create multiple outputs at 5 volts, 15 volts, those kind of things. And also, the output ground and the input ground do not necessarily have to be the same, and that becomes handy in a lot of applications, including the gate drives for other switches. Then we briefly talked about the forward converter, and that's what we are going to continue the analysis today. The topology looks like this. As you can see, it's a little bit more elaborate. Let me just make it a little larger. So as you can see, we still have our one switch. Then all of a sudden we have 3 diodes. And then the windings of the transformer, we have actually 3 of them. The diode number 3 and winding number 3 are used to de-energize the magnetizing inductance of the transformer. We don't really need them if the magnetizing inductance did not exist. And by the way, we don't even need the magnetizing inductance in this case, because the main inductor in the system is this guy over here. Alright, so this is our main inductor. That's what we rely on when we talk about continuous conduction mode or discontinuous conduction mode. We are talking about this particular inductor. This inductor over here is unwanted. Okay, we don't want it, but it's there. We have to take care of it, otherwise it is going to get saturated. And that is why we have added this diode over here, D3, and also this third winding over here. And as we are going to see, the role of these 2 guys is to make sure that the magnetizing inductance is de-energized before we get to the next, basically, cycle, switching cycle. So technically what we want to see is, by the way, this is the analysis under continuous conduction mode, meaning that looking at the current of the main inductor, which is this inductor over here, this current over here, it ramps up and then it ramps down, and again up again. But if you look at the current of this inductor over here, the magnetizing inductor current, we want to keep it operating under discontinuous conduction mode, meaning that it ramps up, then comes back down to 0 before the next period starts. Okay? So we got to make sure of that. Otherwise, what's going to happen is, if you don't take care of this, so this is actually in CCM, this one is in DCM, because if you don't take care of this, what's going to happen is, like, if you eliminate D3 and the third winding, what's going to happen is, let me draw it over here. You get something like this. So this current is going to go to infinity. Obviously, in reality, it's not going to go to infinity. It's going to reach a point that is going to saturate the magnetizing material, the magnetizing material that you're actually using. So this is what we are trying to avoid. All right. We looked at the first mode, so the way we are defining the modes is similar to we have done it before. We consider a period, and then at the beginning of this switching period, the switch is turned on, and we label that to be from 0 to dt. D is the duty cycle, T is the period, and then beyond that, the switch is turned off. Okay. So actually, as it turns out, we kind of can talk about 3 different modes of operation, or maybe 2 modes of operation, depends on how you look at it. But in the first mode, what happens, and that's what we discussed last time, is in the first mode, the switch is on, and we have labeled this over here with this black line over here, like that means the switch is like a short circuit over here. And what's happening is that we have basically circulating current in this loop. That means the magnetizing inductance is getting de-energized. We also looked at this blue loop over here. We wrote KVL for this loop, and we realized that when the switch is on or shorted, there is some negative voltage applied across D3. Therefore, this diode is off. And that's what's meant to be, basically. D3 is not supposed to interact in the first mode. Now we got to look at what's happening in the secondary side of the topology. This is what I mentioned last time, and I'm just going to draw it over here so you guys have a visual, basically, comparison. As it turns out, this topology looks a lot like the boost topology. All right, if you look at this side, on the output side, they are exactly the same. On the input side, they are a little bit different because there is a transformer involved. All right, so if you look at this point to the right, both of these topologies are identical, and as it turns out, towards the end, we are going to realize that the voltage transfer ratio of this converter is like the buck converter. I'm sorry, did I say boost? I meant buck. Okay, so like an isolated buck topology. All right, so let's go to the new notes. All right. So last time we discussed that how this diode is off. We applied KVL around that loop. And remember that L is the main inductor of the system, which is this guy over here. And it is meant or assumed to be operating under continuous conduction mode, meaning that between D1 and D2 at any given time, at least one of them should be on. We cannot have both of these diodes off because if they are both off, then there's no way for the inductor current to flow through anything, and that violates the assumption that this inductor is operating under continuous conduction mode. So between D1 and D2, either they both have to be on, or at least one of them should be on. Now, in the first mode, if you look, the voltage that we are applying to the primary side of the transformer, winding number 1, is Vn. So something proportional with that will appear over here, which is the secondary side of the transformer. So we have this loop that we have some positive voltage appearing over here. Then we have this diode, D1, and then D2. And then we have this inductor that I'm going to replace it with like a current source. All right? So if you look, it's very easy to find out which one of these diodes is on, which one of them is off. Obviously, they cannot both be on because then we are shorting our input voltage source. And as it turns out, D1 is on, D2 is off, because that's the only case that makes sense. If you assume D2 is on and D1 is off, then you are going to realize that there is some voltage drop across D1, which is positive, something like that. All right. So looking at this very simple analysis, you can say diode number 1 is the one that is conducting, and diode number 2 is the one that is off. So basically we have this one shorted. Oops. So we have this one shorted, and this is more like an open circuit. All right. So kind of like the buck converter. I mean, if you look at when the switch is on, it's like D1 is replacing the switch over here. or D1 is affected by the status of the switch. All right, so let me make it a little smaller. Okay, so what we got to do is, in order to find the voltage transfer ratio, we got to look at the voltage drop across the inductor, the main inductor in the system, and then make sure the average value of this voltage is 0. So what I'm trying to track is this voltage drop over here. Okay, so this voltage drop is, right now I know that D1 is on. I know what V2 is, which is the reflection of the input voltage to the secondary side. I know what V2 is. Then I can apply KVL around this loop and find out, okay, and find out what VL is. If you do so, VL turns out to be V2 minus, let me write it over here. VL is V2 minus V out, and V2 is determined by the primary side, which is N2 over N1 times V1, and V1 is Vn, so we have this expression over here. All right, so as far as the main inductor of the converter is concerned, you can argue that there is a positive voltage applied across this inductor, therefore the current of this inductor is rising, similar to the Bach topology. And how do I know that this voltage is positive? I don't know yet, but I would like it to be positive. Then towards the end I have to double check and make sure it is really positive. So what I'm assuming over here is N2 over N1 times Vn is larger than V out, and later we are going to see that yes, it is larger. Alright, so this is what's happening to the main inductor in the system. And for the undesired or the magnetizing inductance, if you look at the voltage drop across this inductor, is actually Vn. Okay, because this switch is on and this voltage drop is the same as the input voltage. Just look at this simple loop over here. Alright, so we can actually again say that this current is rising from 0, and I don't really know if it is rising from 0, but later I have to double check that, and ramps up with some positive slope, and that slope is Vn over Lm, the magnetizing inductance, kind of like a converter in DCM. All right, so this is all about mode 1. As it turns out, when you turn the switch on, both of these inductors are getting energized. Okay, so now let's talk about mode 2, and that is when we turn the switch off. And this is happening for the remaining of the period. As it turns out, I've labeled this to be mode 2, and there's probably a mode 3. So technically what we are doing is, okay, if this is one period, I've labeled this to be T, not some arbitrary variable. So mode 2 is basically from here to here. And then there is a third mode. Okay, depends on which you look at. If you look at the main inductor, we only have 2 modes. Mode 1, energizing, mode 2, de-energizing. If you look at the magnetizing inductance, we have like 3 modes. Energized, de-energized, and it stays at 0. So it depends on how you look at it. So we are looking at mode 2 now. All right, so let's look at mode 2. Let me draw the circuit over here. So we have this diode over here. And let's say, for instance, we have an IGBT as our switch. All right. And then here we have the source. And we shouldn't forget about the magnetizing inductance. This comes here. All right, so something like this, right? All right. So now we know that we have opened up the switch. So the switch is not capable of conducting any current. All right, it's like an open circuit, blocking the conduction of the current. And remember, previously we had this current flowing over here. All right, so ILM was basically this current. So it's non-zero. At the time that we turn the switch off, this current is non-zero. Before it was flowing through the switch. Now it has to flow somewhere else, and as actually it's going to flow through here. Okay, so all of a sudden you realize that I1, which is labeled to be the primary current in this transformer, is not zero anymore. Okay, so I1 is the opposite of ILM. All right. And remember, if you have three windings, all of these currents are flowing in, labeled to be flow into the dotted nodes. Oops, this is I2 and the other one is I3. Okay. So I know I1 is non-zero instantly from the general equation of N1 I1 plus N2 I2 plus N3 I3, which is 0. I know if I1 is not 0, that means between I2 and I3, one of them should be non-zero as well. Otherwise, this equation is not going to be valid. All right, so again, I'm trying to figure out what is happening to these diodes. And in the end, as it turns out, this diode is on, this diode is on, and the one is off. Kind of like the buck converter again. As soon as you open up the switch, the freewheeling diode turns on, which in this case is D2, and D1 is off, and D3 is on. So the job of D3 is to de-energize the magnetizing inductance. Okay, so I have done some basically on this page. You're going to see a bunch of assumptions. What if D1 is on, D2 is off? What is something else? I'm going through the three diodes, 8 different possibilities, and I'm trying to narrow it down. I'm not going to repeat this analysis over here. So basically, what you see on this page is examining different possibilities and see which one of them leads to a contradiction and which one does not. That kind of deal. But as it turns out, D3 is the one that is on, and D1 is the one that is off. Okay. So let's take a look at this. If D3 is on, technically what's happening is ILM is pushing some current to the primary side of the transformer, and if you reflect that to the third winding, it's actually getting as I3 coming out. So let me write the equation over here. Okay, so let's take a look. So in the end, we realize that I2 is 0. If you do the analysis that I haven't done, but it's in the notes, you realize that I3 is negative N1 over N3 times I1. Okay, and what was I1? Negative ILM. All right. First of all, I3 should only be positive because this is also the current of the diode. And as it turns out over here, it is positive. So no violation over there. So I3 is a current proportional with the magnetizing inductance, flows in this direction in a positive way, and supports the D3 actually supports that. So if you really look at I3, what's happening is it is actually sending energy back to the source. So the way I3 flows is it flows over here, comes over here, and goes back to the source. All right, and then from the other side comes out here. So we have this kind of an 8 looking kind of a loop. It's like a loop that is twisted, and it is sending energy back to the source. And where is this energy coming from? It's the energy that we have stored in the magnetizing inductance. We don't need it. We just send it back to the source to make sure the magnetizing inductance is getting de-energized. So if you look at V3, all right, which is this voltage. All right, V3 is the opposite of Vn. It is negative. So if you translate it to the primary side to find V1 and ultimately VLM, which are the same. Okay, so what is V1 now? An ideal transformer, negative N1 over N3 times Vn. All right. So this is the voltage that applies or appears across the primary side of the transformer, which is the voltage that appears across the terminals of Lm, the magnetizing inductance. It is negative, so the indication is this current is going to go down. All right? And by selecting the turns ratio over here, we can select how negative this current should be. So technically, you should make sure N1 over N3 is large, so you're applying a relatively large current, a large voltage across the magnetizing inductance. So before the next period starts, this large voltage de-energizes the magnetizing inductance and pushes the current back to 0. All right. Is this clear what's going on? So we turn the switch on, both inductors get energized, but we don't really care about Lm, we care about L. But in the second mode, when we open up the switch, there is this mechanism of D3 and the third winding to apply some negative voltage across Lm and push this current to go back to 0. All right? So that's what's happening. All right. At the same time, I just made an argument, or I didn't really make the argument. I just said that, okay, D1 is off, D2 is on. Basically, what's happening is, if you look at this main inductor, now if you look at this loop over here, you realize the voltage that is applied across this inductor is the opposite of V out. It is negative. Therefore, okay, so if you look at VL, negative V out, assuming that the output voltage is positive, and later we have to double check that. This is negative, so the current of this inductor is basically ramping down. All right, something like this. All right, so what is this slope over here? This is negative V out over L. That's the slope. All right. What is this slope over here? Negative N1 over N3. Let me see. Yeah, negative N1 over N3 times Vn over Lm. Okay, so this is what's happening. So both of these inductors are basically getting de-energized. Lm is getting de-energized and sending energy back to the source, but the main inductor L is getting de-energized and sending energy to the load. This is what we want to happen. And by the way, for the forward converter, because you're sometimes sending energy back, you got to make sure you have a source that can absorb energy as well, because some sources cannot. Like, for instance, if you have a power supply, there might be some protection circuitry in that power supply. You can't really send energy back to the source. But if it is a battery, it's okay. You can charge the battery a little bit, no problem there. So please remember, sometimes the current of the source could get negative in this case. All right, so this is all about mode 2. Both inductors are getting energized, and by selecting this ratio of N1 over N3, we can make sure that this mode ends before the switch is turned on again. So basically we've got to make sure T naught is smaller than T, and later on we are going to actually have an equation for that. Okay, so just keep that in mind. Now let's look at mode 3. Mode 3 is kind of a continuation of mode 2. Nothing exciting is really happening. The only thing is the magnetizing inductor has returned back to 0, and it cannot really get negative. Why it cannot get negative? Because this diode can only support current in this direction. Otherwise, obviously, things are going to get violated. So this inductor current returns back to 0. And again, that means, okay, switch is off, D3 is off, because its current came down to 0. Again, the question is between D1 and D2, which one of them conduct? And as it turns out, D1 is the one that is on, and D3 is the one that is off. So kind of like the continuation of the second mode. All right, so D1 is off, D2 is on. Okay. And it's really actually easy to conclude that D1 is off. Why is that? Because we just argued that at the end of the second mode, I3 is 0. This current is 0. I1 is also 0. Okay. And looking at this equation of N1, I1 plus N2, I2 plus N3, I3 is 0. I1 and I3 are 0. That means I2 should be 0 as well. That means D1 should be off. Okay. And okay, if this diode is off, if we have non-zero current over here, where is it going to flow through? It's going to flow through D2. So that's how it actually, how you can figure out which one is on, which one is off. All right. So technically what's happening in this mode is nothing. For LM, nothing is happening. The current is remaining at 0. And for the main inductor, again, oops, this shouldn't start from 0, by the way. So what's happening is nothing, just continuation of what was happening. We have negative V out applied across the main inductor, so the slope of the current fall is negative V out over L. That's it. All right, now in this mode, again, so this is for mode 2. In mode 3, again, you can argue that the voltage drop across the inductor, the main inductor is negative V out, it's negative, so nothing really happens as long as the second or the main inductor is concerned. All right. So we analyzed all 3 modes. In the first mode, the switch is on, all diodes are off, both of the inductors are getting energized. In the second mode, D1 is off, D2 and D3 are on, and what's happening is both of the inductors are getting de-energized. LM is getting de-energized through the source. L is getting de-energized through the load, which is good. And then finally in the third mode, the magnetizing inductor current has returned back to 0, so no action is going on over there. D3 is off, only D2 is on, and again the inductor is getting de-energized through the load. All right. So in order to find the voltage transfer ratio, again, what we have done before, I can find this I min, I can find this I max, and find delta IL in the first mode, then delta IL in the other modes, and make sure they are the same. Or an easier way is looking at VL. Okay, VL is the voltage that appears across this main inductor over here. In the first mode, I think we have it up here somewhere. Let me see. In the first mode, it was N2 over N1 times Vn or minus V out. So it's a positive thing, and we have to double check it yet. We haven't done it yet. So this was N, what was that? N1 over N2 or N2 over N1? N2 over N1. Then in the two other modes, it is just negative. And this level is negative V out. All right. So if you make sure on average this voltage drop is 0, because on average the inductor current is neither rising or falling, it's actually fluctuating between the maximum and minimum values. So if you make sure on average VL is 0, what you're going to get is, okay, let's do it. N2 over N1 times Vn minus V out times dt plus negative V out times t minus dt should be 0. All right. So if you just rearrange this, you are going to find the voltage transfer ratio, which turns out to be similar to the Bach topology. The only extra term is N2 over N1, which is the turns ratio of the transformer. And as you can see, there are two observations. One of them is, first of all, this is positive. Okay, so this is positive. That's one of the observations. So it actually makes me happy because I assumed earlier that negative V out is negative. So this makes sense. It is positive and negative V out is negative. The other thing is, the other conclusion that you can make is N2 over N1 times Vn. Okay, this would be actually negative V out. This is going to be positive as well. This is the assumption that we made earlier in the first mode. I assume that this term is positive, and as it turns out, it is positive. So I'm not really violating anything. Everything is good. And this would be our voltage transfer ratio. So this is the forward topology under CCM for the main inductor in the system. All right. So we found the voltage transfer ratio. The next thing that we got to do is take care of the magnetizing inductance and make sure it's actually operating under DCM. So if you look at the current of this magnetizing inductor, it rises from 0, then comes back to 0, and then it stays at 0. All right. Now I'm going to label this to be, I don't know, delta t or delta tx or something like that. Some parameter, something. All right. So we got to make sure that t naught is smaller than t. In other words, before the next period starts, this current has already returned back to 0. All right. And the other thing is, we know that, okay, let me also plot VLM. So this is the voltage drop across the magnetizing inductance, which turns out to be the same as V1, because we are assuming that the magnetizing inductance is reflected all onto the primary side. So this is the voltage we're talking about, this voltage over here. All right. So in the first mode, if you remember, this was just Vn because the switch was on. And it's positive, therefore the positive ramp in the current. In the second mode, it was negative N1 over N3 times Vn. And in the third mode, there is no action going on in the transformer. All of the currents are zero, therefore all of the voltages are zero, so it's basically zero. Alright, so this is a voltage drop across the magnetizing inductor. Again, we know that on average this is supposed to be zero. Alright, so on average should be zero. Okay, this is a little bit tricky thing. I shouldn't really mention on average. I should do something like that. I would say the rise of the current is the same as the fall of the current. Alright, because if you say average, then that Tx thing is going to get involved as well. Although you can say that, yeah, you can say that because it's zero at that level. So on average, VLM should be zero. Therefore, Vn times dt should be the same as N1 over N3 times Vn times the duration of the second mode, that I call it delta Tx. Alright, so this area should be the same as this area. Okay, and please remember I'm talking about areas, they should all be positive. So that gives me an equation for delta Tx, which is the duration of the second mode, which will be N3 over N1 times D times period. So the duration of the second mode is determined by the duration of the first mode as well as the turns ratio of my transformer. Alright. So the thing that I have to make sure of is T naught is smaller than T. So remember, this is delta Tx. This is T naught. This is T. This is dt. Or if you write it in another way, you could say delta Tx should be smaller than 1 minus D times period. Okay. And okay, we have an expression for delta Tx. I just plug it in. Should be smaller than 1 minus D times period. And in the end, you get this expression that you always have to be careful it's not violated, and that is D times 1 plus N3 over N1 should be less than 1. So this is a very important equation. This guarantees the DCM operation for LM. All right. So as we are designing this topology, usually D is determined by the voltage transfer ratio. We don't really have a flexibility on D, but we have flexibility on N3 over N1. So you have to pick N3 over N1 in a way that this equation is happy, not violated. Therefore, your magnetizing inductance is always getting de-energized before the next period starts. All right, so there is an extra equation over here to take care of. So I have a simple, silly numerical example over here just to highlight this issue, and that is, for example, your duty cycle has a range of between 20% and 80% in your system, and all we have to make sure is 1 over N3 over N1 is less than 1 over D. So when it comes to something less than something else, you got to make sure on this side you have the minimum possible value available. Then make sure 1 plus N3 over N1 is even smaller than minimum value. So in order to minimize 1 over D, we got to maximize D. All right. So in this case, I should use the duty cycle of 0.8. Do not use the duty cycle of 0.2. So if you do, you realize that when it comes to selecting or designing your transformer, N3 over N1 should be less than 25% or 0.25. All right. So for instance, if N1 is 20 turns, N3 cannot be beyond 5 turns. It should be less than that. So if in a critical mode, if D times 1 plus N3 over N1 is exactly equal to 1 instead of being smaller than 1, what happens is the magnetizing inductance will be operating under critical conduction mode, and that is T naught and the period will be the same. But I don't really want to risk designing something that we are very close to this region, because if you're just a little bit violating that, then T naught may get greater than T, and as it turns out, you will be accumulating the electric current over here just a little bit. And before you know it, your inductor is going to get saturated. All right. All right. So here we have a bunch of waveforms. These waveforms come in very handy when I'm designing a quiz problem. So in order to test your knowledge of how the different operating modes are, working and what's going on in the system, I may ask all of a sudden you guys to draw me a particular waveform. Here we have all of the waveforms. Let me just go through them very quickly. Let me make it a little larger. All right, we just argued that the main inductor is operating under continuous conduction mode. So it's a typical inductor current starting from I min, going to I max, then returning back to I min at the end of the period. Then we also talked about the magnetizing inductor current, which is in DCM. All right, something like this. And it goes to a maximum value, which is labeled to be ILM max. And we need ILM max because later on it may be reflected somewhere else, so we have to reflect this value. Okay. What about I1, for instance? And what is I1? I1 is this I1 is this current over here. I1 is not something that you can really measure, but in case somebody's crazy and asks you, hey, what is the value of I1, you should be able to just describe it. Then later on, we are going to plot all of these currents. So just have this image in your mind. So I1 is the primary windings current. So remember, in the first mode, I1 was basically proportional. I1 was proportional with the output current. Okay, remember in the first mode the switch was on, D1 was on, so the current of the main inductor was flowing through D1. So if you reflect it to the primary side, so technically what I'm talking about is reflect this current over here from the secondary side to the primary side, and that is your I1. So I min reflected to the primary side is now N2 over N1 times I min, and I max is N2 over N1 times I max. In the second mode, I1 and ILM were the same in opposite directions. So what I'm doing is I'm just going to plot this portion over here, plot it over here in the opposite direction. So it starts from a minimum of negative ILM max, and then returns back to 0, and in the third mode nothing is going on, so this is 0. So it's like a crazy looking current like this. Not that you can really ever measure this current. Okay, so this was I1. What about, let's see what else we have here. What about, for instance, the current of I2? Okay, this is I2, which is the opposite of the current of diode number 1. So we are technically talking about this current over here. Okay, I'm talking about I2, which is the opposite of ID1. Remember, ID1 should always be positive, so this current should always be negative because they are opposing each other. In the first mode, we have conduction going on here. ID2 was the same as ILM. So in the first mode, basically what's happening is all this current that I have over here will be reflected as this current in a negative way. Otherwise, this diode was off, so nothing was going on in the second and third modes. And so this is negative I min, flowing from negative I min all the way down to negative I max, something like that. What about I3? which is the third current. And in the first mode, D3 was off, so no current is going on. In the second mode, the current of the diode was the reflection of the magnetizing current. So whatever current that I have here, I'm just gonna reflect it over there with a negative, with actually a positive sign. Because this is the current of a diode, it should always be positive or zero. In the third mode, nothing going on, and this would be your current waveform. So the reflection is like if the magnetizing inductor current was ILM max, now that is being multiplied by N1 over N3 to highlight this peak value over here. All right, so these are all these three currents of this transformer windings. ID2, the current of D2, which is kind of the freewheeling diode over here. We are talking about this current. Now remember, in the first mode, D1 was on, D2 was off. In the second and third modes, D2 was on, and it was conducting actually IL. So whatever current I have for IL in the second and third modes, that would be the same as the inductor, the diode current over here. So whatever current that I have over here, I just plot it over here. So this would be the current of D2, which is similar to the current of a diode in the buck converter, basically. All right. What about the switch current or the input current? This would be important, and this is actually, I'm sorry, not the switch current. Yeah, the switch current, not the input current, because the switch current and the input current are not the same. So this is the current of the switch. Okay. So if you look at the topology, the current of the switch is the current of the magnetizing inductance plus I1. So that's actually why we bother drawing I1. So this current over here is this current, which is ILM, plus this current, which is I1. So if I have both of these waveforms available, all I have to do is just add them with each other. And somehow we have this, checking point for us, because this switch current always should be positive, and as it turns out it is positive. So basically what I'm doing is I'm adding this current and this current to obtain this current. All right, similar to the current of the switch in the buck topology. It's basically the same. When you turn the switch on, it starts from some minimum value and rises to a maximum value. Then in the second mode and third mode, the switch is off, therefore the current is zero. And these maximum and minimum values are actually highlighted here. The minimum value is N2 over N1 times I min. Okay, so this is adding this zero to this point. On the maximum value, I have to add this maximum value to this maximum value, and I get this larger equation basically. N2 over N1 times I max plus ILM max. So this is the maximum value of the switch. You can see that there is a lot of stress on the switch, more than what we need, because of this ILM max term over there. What about the input current? Okay, the input current is the current that you are drawing from the source. And please remember, it's not exactly the switch current, because this current plus this current is your input current. Or in other words, this current, ILM, plus this current, which is I1 minus I3, is your input current. So if you add all of these waveforms with each other, all right, so the input current is the current of the switch minus the current of the third diode or the third winding. They're basically the same. So technically we are talking about, take this waveform over here, and from it you subtract ID3 or I3, which is basically here. All right. All right. So if you take this current, it gives you these positive levels. Let me draw everything in red over here. and that subtraction gives you these negative values. So altogether you have a waveform like this, which is a little bit different than the Bach topology. As you can see, sometimes this current is negative. That means sometimes you're pushing energy back to your source because you're trying to de-energize the magnetizing inductance. All right. So this is the minimum value of the inductor current reflected to the primary side, which is N2 over N1 times I min. This over here is the same thing plus the ILM max. And then all of a sudden your current jumps back to negative ILM max reflected from the third winding to the first winding. So it's N1 over N3 times ILM max, something like that. What about Vx? Vx is, I don't know if it's really important or not, but anyway, Vx is this voltage over here. All right. In the second and third modes, diode was on, so Vx is 0. In the first mode, Vx was a reflection of Vn, so you get a square-shaped kind of a waveform. Something like this. All right. So when it is positive, it's N2 over N1 times Vn, which is the reflection of the input voltage to the secondary side. And then when it is off, it's just 0. What about Vs, a voltage drop across the switch? So as it turns out, we have to watch for this because sometimes when the magnetizing inductor is getting de-energized, we have a lot of voltage stress on this switch. So we are actually looking at this voltage over here. All right. So technically, if you look at this loop, I don't know what color to use. Let me use this crazy looking one. If you look at this loop, the voltage stress on the switch is related to the input voltage as well as V1. Okay, so it's actually Vn minus V1. So if you consider all the operating modes and try to plot it, it looks like this. First of all, in the first mode, the switch was on, so there is no voltage drop. In the second mode, we had actually relatively large voltage over here, and that's because the magnetizing inductance was getting de-energized, D3 was on, and 1 plus N1 over N3 times Vn is appearing across our switch. In the third mode, we have Vn appearing across the switch because nothing going on in the transformer. V1 is 0, so only Vn appears over here. So please remember, voltage of the switch is Vn minus V1. In the third mode, V1 is 0, so only Vn remains. So this is actually our voltage waveform. All right. And here is our challenge when it comes to designing this converter. Remember, in order to make sure the magnetizing inductance gets de-energized, we had to make sure N3 over N1 is a small value. Like over here, it was only 0.25. That means N1 over N3 is a large value, which is 4. So let me write it over here. N1 over N3 should be greater than 4. Okay? And see where it is hurting us. It's hurting us over here. 1 plus N1 over N3 times Vn is the maximum voltage that our switch should handle. So if N1, in that numerical example, if N1 over N3 should be greater than 4, and let's say you just pick 4, 1 plus 4, 5. So 5 times the input voltage is appearing across our switch when there is this magnetizing inductance that we have to de-energize. So this is actually the trick that we have to play around when it comes to designing the converter. Now, what I have not drawn over here, which could be a good question, what is the voltage drop on D3 or D1 or D2, you know, those kind of diodes? Or we only draw the voltage drop on the switch over here. All right. So we have this numerical example. Let's go through at least the first part very quickly. So we are designing a forward converter, okay? And we are trying to choose a good turns ratio for our transformer and also the duty cycle under these conditions, that the input voltage is 100 volts and the output voltage is 170 volts, okay? So let's review the equations that we had. One of them was the voltage transfer ratio. V out over Vin is N2 over N1 times the duty cycle. The other equation to make sure the magnetizing inductance operates under DCM was D, the duty cycle, times 1 plus N3 over N1 should be less than 1. Okay. So I start and say, okay, first of all, if you look at the output voltage, it is actually greater than the input voltage, 170 volts compared to 100 volts. And duty cycle is less than 1. So if you look at this expression over here, you realize that you should pick an N2 over N1 that is greater than 1. Okay, otherwise you're not going to achieve 170 volts out of 100. And for instance, you randomly choose N2 over N1 to be 2. Okay, something like that. Alright, now that you have selected N2 over N1 to be 2, so we have the output voltage value, we have the input voltage value, all you have to find is the value for your duty cycle, and your duty cycle turns out to be 85%, which is relatively large. So now you are considering the design of N3 or N3 over N1. So you have the duty cycle value and you have that expression. So if you see N3 over N1 should be less than 1 over D minus 1 or less than 0.176. So you choose, again, something smaller than this, not too much smaller than this. You choose N3 over N1 to be 0.1 to satisfy this equation. And everything looks good until you realize, oops, let me take a look at the voltage drop on my switch. So if you look at the voltage drop across your switch, remember in the first mode it was 0. In the second mode it is relatively large, and that is 1 plus N1 divided by N3 times Vn. In this case, N1 over N3 is 0.1. Sorry, N3 over N1 is 0.1. Therefore, N1 over N3 is 10. 1 plus 10, 11, times my input voltage, which is 100 volts. It is 1100 volts. So you have to go to the market and buy a switch that can handle 1100 volts. It's not very easy to find such a switch. And then in the third mode, which it doesn't really matter, it's actually Vn. So you can see that unwanted, you didn't want this to happen, but you are actually applying a very large voltage stress across your switch. So what we are going to do next time is we're going to start here, and considering that we can only have a switch that can handle 250 volts, we are going to redesign the converter one more time. So we are going to have the quiz. After the quiz, the class is dismissed, but please do not get up. And when I ask you guys to raise your sheets when time is up, please raise your sheets and I can collect them all together. And as I said, we have the graded quiz 3. I have it over here, so I can hand it out to you after we step outside. All right, so let's do the quiz.